The purpose of this tutorial is to provide more detail on infiltration and introduce scheduled natural ventilation or natvent simulations prior to covering the more complex calculated natvent simulations in the next tutorial. During the tutorial, I'll discuss outside air infiltration, introduce some key terminology and briefly explain the difference between scheduled and calculated natural ventilation simulations, discuss scheduled natural ventilation simulations, and finally review some of the key simulation results. Infiltration is the unintentional and therefore uncontrolled airflow through the cracks, gaps and porosity in the building fabric and openings. Some of the effects of infiltration can be seen here in the heat balance graph, and here in the total fresh air graph from the simulation results. There are two ways of defining infiltration in DesignBuilder simulations: scheduled natvent simulations, including heating and cooling design calculations, and calculated natvent simulations. I'll describe the difference between the two simulation types shortly. For a scheduled natvent simulation, the infiltration rate is assumed to be constant at a specified value, which is set here in the Construction tab. Going to the Model Options dialog, you can see that scheduled natural ventilation is set by default. And in this case, we can choose to specify infiltration rates in one of 4 different units. You must ensure that you select the correct option for your particular purpose. The first is the default value of air changes per hour under normal atmospheric pressure conditions. The second and third options specify the infiltration rate in meters cubed of air per meter squared exposed external surface at a given pressure differential between the inside and outside of the building. This is 50 pascals in some countries such as the UK and is commonly termed Q50, and 4 pascals in other countries such as France and Belgium. The final option displays infiltration rates in air changes per hour again, but this time at a pressure differential of 50 pascals. This value is commonly termed N50 and is the option used in the Passive House standard, for example. I'll select the Q50 option and then go back to the Construction tab, where you can see that the infiltration rate is now defined in those units. This value can be set by you, or alternatively you can switch infiltration off entirely. This should be done with caution, as it can have a big impact on results, particularly when modelling older, less airtight buildings. Here, for example, is the heating design calculation with infiltration switched on, showing an infiltration heat loss of around 18.6 kilowatts and a total heating load here of around 82 kilowatts. Switching infiltration off and rerunning the heating design calculation results in no infiltration loss and reduces the design heating load to around 63 kilowatts. Before going into the detail of natural ventilation simulations, I'll briefly introduce some concepts that will help you appreciate the fundamentals of ventilation modelling. Ventilation is the deliberate introduction of fresh air, generally to meet the respiratory needs of building occupants, but it can also be used as a means of providing cooling. This can be achieved either mechanically or naturally. Mechanical ventilation systems which supply and often extract air via fans and ductwork systems, are outside the scope of this tutorial. Natural ventilation systems introduce fresh air via openings in the building fabric, i.e. windows, vents and doors, which can be controlled according to temperature set points and operating schedules in the simulation. As highlighted earlier, there are two types of natvent simulation: scheduled and calculated. All the previous tutorials have used the scheduled natvent option when undertaking simulations, primarily for speed and simplicity. Scheduled natvent simulations are generally used for early stage modelling using typical assumed ventilation rates for the building type, but can also be used for more detailed modelling if you have approximate ventilation data for the building, or if the natural ventilation rates are likely to be small relative to other heat flows in the building. Scheduled natural ventilation simulations can also be run using data derived from calculated natvent simulations, which have been undertaken for specific zones in a building, or where you have a mixture of mechanical and natural ventilation systems serving different areas of the building. In scheduled natvent simulations, the ventilation rates are set by the maximum air change rate, modified by the operation schedules in the Activity tab. Infiltration rates are constant and are defined in the Construction tab as shown earlier. Calculated natvent simulations can be used when you have no ventilation data for the building, but are more complex and take longer to set up and simulate. With the calculated natvent option selected, the ventilation rates are calculated using wind and buoyancy driven pressures, opening sizes and operation parameters, and crack sizes. These will be covered in the next tutorial. I'll now go through the key steps required to set up the scheduled natural ventilation simulation. You must first check that the scheduled natvent is set with the required infiltration units in model options. I set this to Q50 earlier. Then ensure that the correct site location and simulation weather data or weather file are loaded. I'll leave these set at this default. For the purpose of this tutorial, I'll assume that this particular building has a hot water radiator heating system with natural ventilation, which I can select from the HVAC template list. You'll notice that the mechanical ventilation and cooling options have been switched off by default. The natural ventilation option is switched on and allows you to define the ventilation rate through the openings such as windows and vents, which are controlled according to operating schedules and temperature set points. You can specify the natural ventilation parameters by zone, where you can set the ventilation rate in each zone using the slider control, or using the minimum fresh air per person option, which is set by the occupancy density and the minimum fresh air setting here in the Activity tab. The by zone method is useful when you have ventilation data that you can use, such as design data or data from separate calculated natvent simulations. Using this method, you can input a ventilation rate at building, block or zone levels. When the minimum fresh air per person option is selected, the slider disappears as it becomes irrelevant. The zone ventilation rates will then be based on relevant data from the Activity tab, which may be derived from National Energy Codes or other appropriate sources. I'll select the by zone method and set the peak ventilation rate to 10 air changes per hour, which would be the ventilation rate used by the model at full occupancy. At lower occupancy periods, such as the start and end of the day, the specified ventilation rate will be reduced according to the percentage occupancy at any particular time. Next, go to the Advanced tab in Model Options and check that the settings here are as required. The option to model airflow through holes and virtual partitions is selected by default, but you'll need to tick the option under the Scheduled header if you wish to model airflow through internal windows, doors and vents. Airflow through interior windows, vents and doors is modelled using the concept of mixing, where equal amounts of air are transferred between zones. The flow rate is directly proportional to the opening area using the airflow rate per opening area. I must check that the infiltration rate in the Construction tab is appropriate for the building type and age. This can differ drastically between buildings, but many national energy codes and standards such as Passive House now have specific criteria for airtightness which can be used to model new and existing buildings. I'll assume that this is a new build which complies with the current UK minimum requirement of 10 meters cubed per hour per meter squared at 50 pascals and set that value here. When running natvent simulation studies, it's very important to check that the set points and schedules on the Activity tab are correct. In particular, when undertaking simulations for energy code compliance purposes, you may need to use the default set points and schedules to ensure that the model data is consistent with the particular calculation methodology. Staying at building level, you can see that the OpenOffice template is loaded, which applies to all the occupied zones in this building. This gives a heating set point of 22 degrees C. The cooling set point is irrelevant, as cooling is switched off in the HVAC tab. Going to the ventilation set point temperature header, you can see that the natvent cooling temperature is set to 22 degrees C, which is the same as the heating temperature set point. I'll leave the set points at their default values to show the potential effects later, but ideally the natvent cooling set point should be at least 2 degrees C higher than the heating set point to reflect the likely control settings in real buildings. This should provide a sufficient deadband to prevent simultaneous heating and venting, i.e. heating using the radiators, which raises the zone temperature above the natvent cooling set point, resulting in simultaneous operation of the heating system and natural ventilation openings to affect cooling. Increasing the number of time steps per hour in the simulation can help to reduce the likelihood of this affecting the results in the model. If you want to avoid temperature control of natural ventilation altogether, you must set a very low natural ventilation cooling set point temperature, such as 0 degrees C. The internal temperature will then always be above the set point, and natural ventilation will effectively operate only according to the schedule. The delta T value is used in scheduled natural ventilation simulations only, and is the difference between the inside and outside air dry bulb temperatures. below which the natural ventilation is shut off. If the indoor temperature minus the outdoor temperature is less than the delta T temperature, then ventilation is not allowed. For example, for a delta T value of 2 degrees C, ventilation is assumed to be available if the outside air dry bulb temperature is at least 2 degrees C cooler than the zone air temperature. If the outside air temperature is warmer than this value, then ventilation is automatically turned off. This option enables you to prevent excessively warm outside air heating the occupied zones. If you want to avoid temperature difference control of natural ventilation, you must set a high negative value for delta T. The default value of -50 will therefore allow natural ventilation to be enabled according to the set point and operation schedule without consideration of outdoor air temperature. Note that the same principles apply to both scheduled natural ventilation and mechanical ventilation. So care should be taken not to prevent adequate ventilation in occupied zones if changing the delta T value. The natvent operation schedule here is more likely to be set at building or block level, as the natural ventilation control strategy is likely to be considered only for the whole building or significant parts of it which have different occupancy times or operational criteria. For that reason, the operating schedules are not set by the activity template loaded for the zone, but are inherited from the activity template set at building level, unless a different schedule has been loaded at a level below that. You can either select a schedule from the extensive existing library or create your own. Occupancy-based schedules are generally used for natvent control, particularly when there is no automated natvent control system in the building, as occupants often open windows and doors to reduce internal temperatures. As this is an office building, I'll keep the open office occupancy schedule set at building level. To summarise, scheduled natural ventilation will be enabled under the following circumstances. When the operation schedule is on at that particular time in the simulation, and when the air temperature in the zone is higher than the natural ventilation cooling set point temperature, and when the difference between inside and outside air temperatures is less than the natvent delta T. I've just run a quick summer typical week simulation so we can have a look at some of the information relative to the natvent input parameters. You can see immediately the impact of having the same heating and natvent set points, resulting in the windows opening to allow heat from the heating system to escape. I've rerun the simulation with a 20 degrees C heating set point to provide a 2 degrees C deadband and prevent that problem. Looking at the total fresh air graph at the bottom, you can see that infiltration provides a constant and uncontrolled air change rate of about 0.1 air changes per hour. The fresh air natural ventilation rate increases with occupancy and follows the occupancy profile until such time as the natvent cooling set point is reached. The natvent rate increases as the room air temperature increases and reduces when the room air temperature drops below the natvent cooling set point, as is best seen on Wednesday and Thursday here. You can see the warmer outside air temperature on Friday results in higher room air temperatures. Therefore, the ventilation rate on Friday follows the occupancy profile for most of that day. The internal gains graph here shows the correlation between the ventilation rate and the associated removal of heat or the cooling effect from the natvent openings. This can be seen more clearly by changing to the single day view. Scrolling to Monday, you can see that there's a degree of ventilation control here in the morning at lower outside air temperatures. The natvent control enables the full 10 air changes per hour at full occupancy as the outside air temperature rises in order to keep room temperatures down. This tutorial has provided all the information necessary to undertake a scheduled natural ventilation simulation. I'll build on this information in the next tutorial, which covers the more complex calculated natural ventilation simulation.